Hello, today we are going to discuss vector model under atomic molecular physics. So we are going to discuss it from the point of view of exams for Ph.D. So we won't be discussing the theory in details. We would be rather concentrating on solving problems. So today's topic is vector model, and we're going to discuss some basic notations and some formula before we solve some simple problems. Now the orbital quantum number is given by L, and the component of the orbital angular momentum ml can take the values minus L to plus L. Similarly, we have spin quantum number s, and the component of the spin along any particular direction, say the z axis, can take values from minus s to plus s. Then we have the concept of total angular momentum J, its vector. So this semi-classical approach. So J is equal to L vector plus S vector. So J vector is represented by, J is also it's an angular momentum, and it is given by the quantum number J, and the component of J along any particular direction can take the values minus J to plus J in steps of 1. So if the orbital quantum number is L, and let's change the color. Okay, so if the orbital quantum number is L and the spin quantum number is S, then J can take the values L minus S modulus to L plus S in steps of 1. So these are the possible values of J. Now we have 3 vectors. So this is a vector model. So this is called the vector model. So this is a vector, this is a vector, and this is a vector. Let me change the color. So this is a vector. So if we consider the angle between, say, L vector and S vector, then cos theta ls is given by this expression, and this you can easily obtain. You just have to square it. You just have to square it and you will get the answer. So it's like J square is equal to L plus S whole square, and then we have, so this is equal to L square, we know, L vector square plus S vector square plus twice L dot S. So this is how you approach it. So from here you get this. So we know this is typically L into L plus 1 H bar square. So this is also, we know, S into S plus 1 H bar square. So like that, if you do, you get cos theta ls. Similarly, you can get the angle between J vector and S vector, and this is the expression. And similarly we can get the angle between L vector and J vector. For this is the expression cos theta Lj is given by this expression. We are going to use this expression later on. Similarly, now we go to what is called magnetic moment. So when there is angular momentum, means like orbital angular momentum, or you have spin, then we can associate a magnetic moment because it's the electron that is spinning or participating in the orbital angular momentum. So the mu L, so this is actually a vector quantity. Mu L vector is minus GL E by twice m. M is the mass of the electron, E is the charge of the electron, and this is the orbital angular momentum of the electron. So the orbital, so this is the magnetic moment corresponding to the orbital angular momentum L. Similarly, if the spin is given by S, then the spin magnetic moment is minus gs E by twice m S vector. Similarly, when we have a total angular momentum J vector, then we can define what is called the total magnetic moment mu J vector, and that is equal to minus G J E by twice m J vector. So GL is actually 1, this GL, GS is 2, and this is the Landau factor, Landau G factor. So this can be found out, and it comes out to be 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by twice J into J plus 1. Okay, yeah, I think it is, maybe there is mistake. Okay, so this is the expression for Landau G factor. And if we introduce a magnetic field B in the system, then the orbital angular momentum precesses about the angular momentum. The orbital angular momentum precesses about the magnetic field B with a frequency which is called a Larmor frequency, and that is omega is equal to Eb by twice m. E is the electronic charge, B is the magnetic field, and m is the mass of the electron. So this is the Larmor frequency. This is the frequency with which the orbital angular momentum precesses around the magnetic field. Now, if an atom is exposed to electromagnetic radiation, then there will be a transition between energy levels. So that is called electric dipole transition. So that transition has some selection rules. So any transition is not possible. For transition to take place between energy levels, delta L, that is the change in the angular momentum quantum number, should be plus minus 1. Delta M, that is the magnetic quantum number change, should be 0 or plus minus 1. And the total angular momentum quantum number change should be 0 or plus minus 1. And there should be no change in the spin quantum number. What is important in this case, in such transition, is that there has to be a change in parity of the wave function. That is, the transition should be from, say, an even function to an odd function. A transition from even function to even function is not allowed, it is forbidden. Or the transition should take place from an odd function to an even function. A transition from odd to odd is not allowed. So there should be a change in parity of the wave function, and that is governed by the selection rules. So this is a very simple problem. So which of the following electric dipole transition is not allowed in the case of an atom? So there are 4 options, and you can see that this option clearly, this option is not, this is the option because this transition is forbidden, because delta L is equal to from D to S, so delta L is equal to 2. So this is not allowed by the transition rule. Now we go to another problem. So here the possible values of multiplicity X in the spectroscopic notation. So this is a spectroscopic notation of energy level. So X, F1 R. So what are the possible? So here X is given. So let me change the color. So what are the possible values of X? Okay, so what are the possible values of X? So there are 4 options. X is what you call the multiplicity. And what is X? X is 2s plus 1. S is the spin quantum number. Okay, so here what is F? F corresponds to L is equal to 3, isn't it? And this is the value of J. This is the value of J. So J can take the values 3 minus S modulus to 3 plus S. And we know that one of the values of J is 1. So S has to be so chosen so that there will be J. So there will be one value of J which is equal to 1. So if you do this, so you will find that there are 3 possible values of S, and for each value of S you can calculate X, and from there you can calculate, we will see that the first option is correct. So the possible multiplicities are, so X can take the values 5 or 7 or 9. Next we go to another problem. Consider the states in which L is equal to 4, S is equal to half. So consider the state with the largest value of J and Mg. Show that the angle between L and S is arc cos 2 by root 15 or cos inverse 2 by root 15. And then we have to show that the angle between J and for this Z, for this maximum Mj is, and the J axis is arc cos 3 by root 11. So we have to find out the largest value of J, and once we find out the largest value of J, we can find out the largest value of Mj. And this is also not difficult. So J can take the values 4 plus half to 4 minus half. So easily we can see that what can be the largest value of J. So this will be the largest value of J. And once we have the largest value of J, we can also find out what is the largest value of Mj. So from here we can find out cos theta ls. Okay, we know the value of J, largest value of J. So this is corresponding to the largest value of J. So we have already seen this expression. So we just have to use this expression to find out cos theta ls. Similarly, we have to find out cos theta zj. So this will give the angle between the z axis and j for the largest value of mg, and that is also very easy to do. Once we find out j, so here is clear, the largest value of j is 9 by 2. Okay, and this is the largest value. This is j max, this is J max, and similarly what, so Mj, the largest value of Mj will be also, Mj can take the values minus 9 by 2 to plus 9 by 2, so here it will be 9 by 2, simple. So once you get this, so J into J plus 1 H bar cos theta z cos theta z j is equal to your Mj H bar. We know this, so from there we can easily find out cos theta zj. We go to the last problem. So we have to find out the Landry factor for a singlet state. So we have to show that the Landry factor in the singlet state is 1. Singlet state corresponds to S is equal to 0, isn't it? So multiplicity is given by 2s plus 1. 2s plus 1 is multiplicity, and if S is 0, then its multiplicity is 1, that is a singlet state. And for a singlet state, J and L are identical, and then we just have to substitute in the expression for this GL, and we'll get the value of Landry factor. So we'll end today, and we will go to more advanced topics very soon. Thank you.